Okay, let's say that you have let's just introducing Newton's second law problems. Let's just say, for example, you have a chair sitting on a floor. It's actually supposed to, its legs are on the floor. And the chair has a mass of 12 kilograms. And I want to know all the forces, what are the forces on the chair, and what are their magnitude? Or let's say magnitude and direction on the chair. So the chair is on the floor. The only thing it's touching is the floor. And if there wasn't a floor, the chair would be doing what? It would be accelerating downward. Let's say it's on the second floor of a building and there was no floor. The chair would be accelerating downward towards the surface of the earth, which it's not doing because the floor is holding it up. So the floor is exerting an upward force on the chair. The floor is exerting an upward force on the chair. So how do we indicate that? What we want to do is we want to take the chair out of the picture. Let's just say this is my chair, or let's just make a dot. This is my chair, right? Let's just represent it by a dot and say that the floor is pushing upwards on it. That is the force that the floor is keeping the chair from moving through the floor. That's the only thing touching it, so that's the only thing exerting a force. I'm sorry, careful. That's the only thing touching it exerting a force. And then, of course, there's always the gravitational force. Everything has weight. So there's the gravitational force. And the gravitational force is always equal to mg. And it's, in this case, downward. So those are the forces on the chair. We can go ahead and choose a positive direction. You could do this problem really without choosing a positive direction. But I'm just going to choose, let's say, up as my positive direction. And we can go ahead and apply Newton's second law. We can say that the net force, the sum of all the forces on the chair, equals the mass of the chair times the acceleration of the chair. So therefore, right, look at the net force. There's the floor force upwards. So that is the floor force, which, by the way, I don't think I said, is a normal force. The floor force upwards and the gravitational force downwards. So it's the direction of the force goes before the force, right? And then this is just the magnitude of the force. So plus F floor minus Fg. So now this is how I'm plugging into F net, right? F floor minus Fg. There's F floor in the positive direction, Fg in the negative direction, and I'm explicitly putting those signs in there and there. Okay, and we set that equal to ma. And we say, oh, but the chair is not accelerating. It's not going anywhere. It's zero. So you can see, and this is where you could have done this without explicitly applying Newton's second law, probably. I don't know why I keep on doing F. Oh, I know why I'm doing F floor, because F is F. You get it. Maybe you get it. I don't know. It doesn't matter. F floor minus Fg equals 0. So therefore, F floor, the magnitude of F floor equals the magnitude of the weight. So the magnitude of this force equals the magnitude of this force. The fact that they're in opposite directions was already taken into account. Okay, so what are the forces, magnitude and direction on the chair? They are the weight downwards, and that's equal to mg, which is Fg equals 12 kilograms times 9.8 meters per second squared. That doesn't mean it's accelerating downwards. It's not accelerating downwards. That's just its weight. That's how heavy it is. It's mg. It's 117.6 newtons, and therefore F floor must also be 117.6 newtons, but it's up. Right? The weight is down and the floor is up. Okay. So that's the vector F floor. Now remember, I called the force the floor exerts on the chair F floor. It's really F floor on chair, or the normal force on the chair. So now what if somebody sits in the chair? Let's have you come along and sit in the chair. So this is you, and you're going to sit in the chair, or at least you're going to be, maybe it's a really giant chair, so you're going to stand on the chair. It's a giant chair that doesn't have a very large mass. And let's say that your weight is 100 Well, now let's give it in newtons just so we don't have to do unit conversion. Let's say your weight is 400 newtons. You're not a terribly heavy person. I'm 600 newtons. So your weight is 400 newtons. And now let's ask, what are the forces on the chair? Same question. What are the forces on the chair? Part A was with nobody on the chair. Part B is with you on the chair. Well, so again, let's draw a diagram, what's called a free body diagram of the chair. And we're going to say, okay, well, it's still, the floor is in contact with the chair. And I keep on doing F sub L-O-O-R, F floor, F G. But you are also exerting a force on the chair, your force on the chair. Fu on chair. Okay, so there are 3 forces on the chair. And Fg is still the chair's weight, 117.6, was it 117? So yeah, 117.6 newtons, and that's down, that's the weight. Fu on the chair, what force do you exert on the chair? Because you're not accelerating, you are just exerting your weight on the chair. So Fu on chair. Whoops, this is not working. You're just exerting your weight downwards. You're sitting on the chair. That's how hard you're pushing on it. How do I know that? Is a Newton third law argument, which we'll come to later, but I think it's reasonably clear that you're pushing down on it with a force equal to your weight, 400 newtons down. And what is the normal force? The floor force, the floor on chair, which is the normal force due to the floor. The normal force is now, is it still 117.6 newtons? It was 117.6 newtons here. No, it's bigger, right? It's now 517.6 newtons up. Because now the normal force is holding up both you and the chair. The normal force is holding up both you and the chair. So you still have to look at this, and I mean, if you don't see that immediately, you still have to do F net equals ma of the chair. The net force on the chair is the floor force upwards. Let's choose up as my positive direction. The floor force upwards minus your force downwards minus Fg downwards, right? Those two are down, so I'm just going to say minus, the vector is going to be minus the magnitude Fu minus the magnitude Fg equals mass times acceleration, 0. So therefore, F floor is equal to Fu, plus Fg. And so it equals 517.6 newtons up. What I wanted to show here was a basic how to solve Newton's second law problem, how to take into account the vector nature of the forces by putting the signs in front of the magnitudes. But I also want to show that the normal force, the floor force, which is a normal force, is not a fixed number. There's no equation for the normal force. The normal force is solved from Newton's second law. It depends. It's a reaction to what's pushing down. So if it's just the chair, it's 117.6 newtons upwards, the normal force. But if you're pushing down on the chair, then it's 117.6 newtons upwards plus the amount of force that you're pushing downwards on the chair with. So the normal force is what's called a reaction force, right? The normal force. And we'll talk about this a little bit later if we haven't already talked about it. Normal force is, what do I mean by it's a reaction force? Meaning there's no formula for it. It reacts to the other forces in the problem. The only way you can know what the normal force is to solve for it from Newton's second law. Right? There's no formula for it, like there is for Fg. Fg is mg. The gravitational force is just mg. But the normal force doesn't have a formula. It has to be solved from Newton's second law.